The topic of this lecture is important theorem of Riemann integration part 3. So we'll cover these two theorems in this lecture, first fundamental theorem of calculus and second fundamental theorem of calculus. So let us see the statement. First fundamental theorem of calculus. It says that if f is continuous on closed and bounded interval ab, and if fx is equal to a to x ft dt, then f dash x is equal to fx, that is derivative of f with respect to x of capital F is equal to small fx for all x lies between a and b. So that we are going to prove. So let us see the proof. For any fixed x belongs to a b, if we take any fixed x and if h is not equal to 0 such that x plus h is also point of ab, then we have, because we are given this fx plus h minus fx, that will be a to a plus h ft dt minus a to x ft dt, and from this two we obtain that it is integration from x to x plus h ft dt. We call it equation number 1 using the property of definite integral. So this is clear that this is equal to this expression that will be used later on. Now, as f is continuous on closed, and bounded interval x plus h, x to x plus h, because it is given it is continuous on AB, and this is a sub interval of A to B. So f attains maximum value, say capital M, and minimum value, say small m, at some points of x to x plus h. So there exist points, we say t1 and t2 of this interval, such that f t1 is equal to m. At some point t1 it will attain the value small m, and at some point t2 f will attain the value capital M, and the general value ft will lies between small m to capital M. Now, taking integration from x to x plus h, so this inequality holds over here also. So we get x to x plus h m dt is less than equal to x to x plus h ft dt is less than equal to x to x plus h capital M dt. And from this, because x to x plus h m dt, m is constant, so it will be h times m, and x to x plus h capital M dt, m is constant function, so it will give m into h. So from this we obtain, we get finally that mh is less than equal to x to x plus h ft dt is less than equal to capital M into h. So this we have obtained. This we'll call equation number 3. So because this holds, so we can find a value theta such that m is less than equal to theta less than equal to capital M, and the value of theta is equal to 1 upon h x to x plus h ft dt. How we are obtaining this? We are obtaining this from here, because if we divide all the side by h, so this will be m times the value less than equal to 1 upon h times is less than equal to capital M, where h is not equal to 0. So this we are denoting by theta over here. Now since f takes every value between m and m, so by intermediate value theorem of continuous function, we can find a point ch depending on h, which lies in x plus h, such that the value of f at ch, that will be equal to theta. That is, the value of f at ch will be this value. Thus, if h is greater than 0, there exists a ch depending on h c, which lies in x plus h, such that the value of f at c is equal to 1 upon h x to x plus h ft dt. Now by 1, what is 1? What was 1? This is 1. F x plus h minus fx is x to x plus h ft dt, we get that fx plus h minus fx by h is equal to f at ch, that is value of f at c, which is depending on h. Now as this, where is this c lies? It lies between x to x plus h. So as x is less than equal to ch and ch is less than equal to x plus h. So when we take limit h tends to 0, we get, because here from this expression when we take limit h tends to 0, c becomes x, that is the value of this limit is equal to x. And since, because f is continuous at x, so when we take this limit h tends to 0, fch, that is nothing but fx. So from this fourth one, taking limit h tends to 0 on both sides, the left hand side will become the value f dash x on, and the right and this is equal to limit h tends to 0 fx plus h minus fx by h, and the right hand side fch, this is will be equal to small fx. So we have proved that the f dash x, capital F dash x, is equal to small fx. In the above proof, we took h is greater than 0. In place of this, if we take h less than 0, we can start with the interval x plus h to x, because h is less than 0, instead of x to x plus h. And by suitable modification, we can prove the theorem in that case also. So by this way, this theorem is proved. Now let us see what is the mean by primitive or antiderivative. A function f is called, capital F is called primitive or antiderivative of a function f on a closed and bounded interval ab if f dash x is equal to fx for all x belongs to ab. That is, if f dash x is equal to, say, small f x, then this capital F is called the primitive of or antiderivative of small f. So that is the definition. Now let us see the second fundamental theorem, which is based on this. So if f is continuous function on closed and bounded interval ab and phi dash x is equal to fx, that is, in this case phi is antiderivative of f or primitive of f for all x belongs to AB, then integration of f or AB is equal to value of phi at B minus value of phi at A. So let us see the proof. This we have to prove. So let us start with capital Fx is equal to A to x ft dt, as we have seen in the previous theorem also. So since f is continuous, so by first fundamental theorem, this will implies, from this relation, we obtain that f dash x is equal to fx for all x which lies between a and b. That we have seen in first fundamental theorem. Because if this holds, then this will also hold. But what is given? That phi dash x is equal to fx. That is, phi is given as a antiderivative of fx. Hence, from this two relation, from this and this one, we obtain that f dash x is equal to phi dash x for all x lies in closed interval ab. But this implies, because of these two functions derivatives are equal, so this implies that fx is nothing but phi x plus c for x lies between a and b, where c is any constant, a real number, a constant. So, but because of this, let us start with fb minus fa. What will be this fb? Using putting x is equal to b over here in this relation, we get phi b plus c, and putting a in this relation, we get phi a plus c, and c cancel, so we get phi b minus phi a. But what is the value of fa? The value of fa, when we find from this, it is a to a ft dt, and its value is 0. And what is, so its value is 0. Now let us see what is the value of FB. So the value of FB will be 5B minus 5A from this, because FA is 0. So we get FB is equal to 5B minus 5A. But what is the value of FB? FB from this relation, that will be A to B FT dt. So we conclude, because FB is this, so we conclude that A to B FT dt from here and here we obtained that A to B FT dt is 5B minus 5A. So by this way, this second fundamental theorem is also proved. Sometimes it is asked that state and prove second fundamental theorem. So we will have to write the statement and the proof also. So thank you very much. You can find the link for this PPT in the description box. Thank you very much.